Among the thousands of lifeless planets, it's impossible to find one as picturesque and alive as the Earth, which seems to violate the very laws of the cosmos. All life that has ever appeared on this planet owes its existence to water. The first complex molecules, the first organisms, the first humans, all of them have their roots in water. But how did so much liquid water appear on Earth, among desert planets? For all of science, the place of origin of water remains a mystery. Whether water originated in the hellish bowels of the young Earth or millions of light years away in inaccessible depths of space is a confusing question for all scientists. But the closer we get to the solution, the closer we will get to answering the question, are we alone? Today we'll try to find the sources of water and life on our planet, diving into the very beginning of the solar system and find out why water chose the Earth, saving it from the fate of Mars and Venus. Approximately 70% of the Earth's surface is covered by water. The imposing number of bodies of water on the planet seem to us to be something quite ordinary, and based on what we know about the birth of planets, the Earth should have been completely dry. Let's go back to the very beginning of the life of our solar system. We're looking at a young sun, which has just formed from the remnants of an ancient supernova, which left a giant plume around it, a protoplanetary disk of dust and gas that spread over hundreds of millions of kilometers due to nuclear processes in the star. Many of the planets we know today, including the Earth, will be formed from these building blocks in billions of years. Since the only materials that could exist around the Sun at that time were stone and iron, the four nearest planets were formed from them. According to a recent study by the California Institute of Technology, the planetesimals from which the Earth was formed consisted of dry, stony materials. These building materials did not contain volatile substances such as water. In particular, gas was unavailable in the early stages because it was mostly ejected beyond the orbit of Mars, so an atmosphere was out of the question. But wait, what does the atmosphere have to do with it? In the early days, the Earth did not have a moderate temperature as it does now. The disk was very hot, and the Sun was very active, which is why instead of water, seas of magma were pouring out on the planet under deadly UV radiation. Therefore, there was no way that water could be retained on such a hot Earth in liquid form. And because there was no atmosphere, water could not accumulate as steam. The magmatic period could have lasted for several tens of millions of years until the surface cooled down. And, according to many studies, including those of the University of Chicago, water began to appear after that. But how did that happen? The Earth couldn't have formed with an ocean because it would have boiled over due to the hot protoplanetary disk. It would have become a scorched, dry planet like Venus, for example. Instead, water spilled into its interior, which created the conditions for the emergence of all life that exists today. So how could water get to the dry Earth? Perhaps the answer to this mysterious question is right above us. Water could have been brought to Earth by extraterrestrial messengers traveling through space. No, we're not talking about alien life forms, but ordinary comets and asteroids. In a groundbreaking study conducted by scientists using NASA's Stratospheric Observatory for Infrared Astronomy, SOFIA, water was first detected on the surface of the asteroid Bennu. The presence of water molecules in the rocks of Bennu indicates that such asteroids could have delivered water to Earth in the early days of the solar system. The discovery was made possible thanks to SOFIA's unique capabilities, which include a powerful telescope mounted on a Boeing 747 SP aircraft. By flying over 99% of the Earth's atmospheric water vapor, SOFIA was able to capture infrared waves that are otherwise blocked, allowing for precise observations of the composition of Bennu's surface. Comets are composed of frozen gases of rocks and dust and orbit the Sun in highly deformed elliptical orbits. They're actually snow comets that carry a lot of water and other building materials, such as methane, ammonia, and carbon dioxide. As they approach the Sun, comets melt, releasing clouds of water vapor that are captured by the Earth's gravity. Asteroids are the remnants of the primordial solar system during its active formation. They also had a significant impact on filling the Earth with various important elements, such as silicate rocks, iron, nickel, etc., depending on the class of composition. For example, the most common, chondritic asteroids, or Class C, have up to 13.5% water in their composition, the molecules of which could be transported as space dust. Therefore, it seems very likely that comets and asteroids may be behind the global appearance of water on Earth. The carbonaceous asteroid Bennu is considered to be a time capsule from the early solar system, containing valuable clues about its formation and evolution. The discovery of water on Bennu adds to the growing body of evidence that carbonaceous asteroids may be important sources of water and organic compounds essential for life. The presence of hydrated materials on Bennu, which form in the presence of water, suggests that Bennu's parent body had liquid water in the past. This also means that Bennu, or similar asteroids, could have been water carriers to the early Earth, contributing to the formation of the planet's initial water supply. In particular, in the period from 3.8 to 4.1 billion years ago, the inner planets of the solar system experienced a strong bombardment by asteroids and comets, better known as the Late Heavy Bombardment. This event may explain the abundance of water on the planet, but it still requires in-depth research, such as the craters on the Moon, which were probably left by the bombardment. The atmosphere also did not stand in the way of these travelers, so asteroids and comets freely entered the Earth's space, accumulating the first water. According to the research of space chemists led by Nicolas Dauphaz, about 10% of water could have been brought to Earth by comets and asteroids. Along with asteroids and comets, meteorites are another candidate. Meteorites are fragments of asteroids or comets. The most likely source of water could be molten meteorites, which have been floating around since the formation of the solar system. However, recent studies of this type of meteorite have shown that they have a very low water content. But all is not lost for meteorites. There are several other types, including carbonation chondrites and enstatite chondrites. Despite their complicated names, these two species are currently considered to be the most likely source of water on Earth, as they contain up to 20 on average, and could even bring 3 times as much water to Earth as our oceans have now. Over time, as the Earth cooled and geologic activity decreased, it took the first steps toward the developing plate tectonics. The movement of these plates formed new mountains and ocean trenches, contributing to the system of water transfer from rivers to oceans. Plate tectonics also allowed water to be stored in the Earth's evolving mantle, motivating geologic activity and thus the formation of water within the planet. Constant bombardment by cosmic bodies also continued to fill the Earth with water. Thus, water arrived on the Earth almost continuously, gradually covering its revitalized surface with water. The still young Earth, which was just beginning its active internal formation approximately between 2.5 and 4 billion years ago, did not have sufficient opportunities to drain water into, for example, the mantle, due to its limited capacity. Therefore, the combined efforts of asteroids, comets, and internal activity could have completely covered our Earth with water, making it a complete water world without a hint of land. In 2021, scientists from Harvard University, led by Junji Dong, conducted a geochemical study of the planet's water reserves. To their surprise, it turned out that the Earth's original ocean could have been 1 to 2 times larger than it is now. According to Junji Dong, this ocean could have flooded 70 to 90% of the early continents. A group of scientists calculated and compared the approximate amount of water in the mantle today and billions of years ago, and found that the ancient mantle could not hold as much water as it does now. This means that residual water would have to be stored on the Earth's surface. This theory can change our entire understanding of how the ancient Earth developed and, in particular, all life. Currently, theories about the origin of living organisms in shallow ponds with a mixture of different minerals and building blocks on land or in hydrothermal substances at the bottom of the ocean are popular. However, the global ocean may upend these assumptions, requiring new explanations of how life came to be or a revision of what we know about the conditions for its formation. For example, scientists are already putting forward the first theories about where organisms evolved. Thomas Carroll believes that protected water pockets in oceanic rocks may be the answer to this question. Yet, if the Earth had remained a water world, the continents and life forms we know would never have formed. The delicate balance between the water brought by asteroids and comets and the Earth's tectonics has made the planet ideal for habitation. And if there was too much water or too little, Junji Dong says, nothing would work. But only extraterrestrial space bodies could not form and maintain an ocean for a long time. Venus and Mars also experienced bombardment, but they failed to retain much water on their surfaces for a long list of reasons. And one of these reasons is the location and temperature regime in the solar system. As long as Venus is too close to the Sun and Mars is too far away, the Earth seems to be in an ideal place to maintain water in liquid rather than gaseous or solid forms. Such a place in planetary systems is called the Goldilocks zone. This zone, which is most suitable for the emergence of life, differs in each system depending on the type of star. For us, it exists between 0.99 AU and 1.7 AU, right on the edge of the zone. Without the Goldilocks zone, the water that comes to us through external pathways would evaporate or turn into ice. Moreover, the ideal zone maintains the water cycle, regulating weather and climate, and balances the functioning of ecosystems. The Goldilocks zone played an equally important role in the formation of the Earth as a habitable planet, supporting and storing water and all the additional elements brought from outside and formed within the Earth itself. All of the above theories and assumptions require careful and serious research to finally establish the full story of water's origin. The recent discovery of Bennu emphasizes the importance of ongoing research to understand the origin of water on Earth. Such research not only supports existing theories, but also provides new knowledge and evidence, deepening our knowledge of the early solar system and potential sources of water. Missions such as OSIRIS-REx, which collected samples from the surface of Bennu, aim to return these samples to Earth for detailed laboratory analysis. These samples will provide unprecedented information about the mineralogical and chemical properties of Bennu, further illuminating its role in the history of the solar system. But in fact, researching this issue is by no means an easy task. First of all, the water that scientists are most interested in is hidden deep underground under the oceans. The water is likely to have a different composition than seawater, so it would be possible to find out exactly what the main sources of water were. Therefore, scientists are probably currently using the wrong DH, deuterium to hydrogen ratio, for the Earth, which is the main method of comparing the chemical composition of the Earth and other cosmic bodies. However, it's still extremely difficult to get to the mantle. Although scientists have already had some success in this direction, having drilled a mile under the floor of the Atlantic Ocean for the first time, where they retrieved the first pieces of the mantle. But full-fledged and high-quality water studies are still far from being conducted there. Despite this, the difficulty is further complicated by the insufficient sample of comets and asteroids to study the correlation between their chemical composition and water bodies on Earth. The protoplanetary disk around the Sun, as it moves away from it, has a completely different ratio of deuterium to hydrogen in its composition. Therefore, it's difficult to determine where the space body that brought the water could have formed in order to better understand its composition and amount of water. In addition, the diversity of water sources requires a multifaceted study to determine the contribution of each group of objects. To solve this problem, it's only necessary to study several space bodies at different distances to determine which population of space bodies is responsible for water on the planet. But today scientists can only measure the closest and brightest objects. The water on Earth itself can also confuse the trail due to changes in its composition over millions of years. The search for what filled the Earth with water will take a long time, but gradual improvements in analytical methods and future research missions will one day shed light on the sources of our life, including our own. Scientists continue to work in the hope of advancing our understanding of how water got into the solar system. In 2021, cosmochemist Laurette Piani from the University of Lorraine analyzed a very rare type of meteorite called enstatite chondrite. The isotropic composition of this meteorite is similar to that of the Earth, and it's likely to be a remnant of planetary material from the outer solar system. According to the study, these meteorites could have brought 3 times as much water to Earth as our oceans have now. Moreover, the isotopes of hydrogen and nitrogen on enstatite chondrites match those found in the mantle, which also indicates that most of the atmospheric air could have come from these rocks. However, the composition of seawater does not quite match that of meteorite water. It is possible that other space bodies could have mixed with the water, changing its original chemical content and confusing scientists. On the other hand, a group of scientists led by Edward D. Young put together a completely unexpected theory that could move space objects from the first place in the group of the main sources of water on Earth. Most of the water could have appeared on the planet from former magma oceans, where oxygen interacted with hydrogen in the early atmosphere. The interaction of magma and hydrogen produces water. This amazing process does not negate the impact of asteroids, comets, and meteorites, but rather adds to the history of water on Earth. Finally, in June 2023, another stunning theory emerged that goes against what we know about the formation of the Earth. According to this theory, instead of water appearing on Earth due to cosmic bodies, our planet was attracted mostly by pebbles and ice particles from the protoplanetary disk in the early stages of its existence, like a vacuum cleaner. Thus, the presence of water doesn't depend on a random event like comet bombardment, according to lead author Isaac Onyett, and therefore the Earth could have formed in as little as 3 million years instead of hundreds of millions of years. This theory could overturn all knowledge about the formation of planetary systems and the origin of water in particular, so it needs a lot more careful research to make its mark even louder. The history of water on Earth is one of the most intriguing questions for modern science. Scientists propose many theories and assumptions based on studies of samples as old as the Sun itself, getting closer to the desired solution every day. Whether brought by comets, meteorites, and asteroids, or formed by the Earth itself, water is fascinating for its mystery and ability to shelter and sustain life. And one day, its mastery will be tamed, and we will finally know how the Earth came to life. What if the colors we see in the night sky are just the beginning of a story yet to be told? Our documentary invites you on a journey of discovery, where each chapter unfolds the hidden narratives of distant worlds, challenging what we thought we knew about our universe. First, we dive into the azure depths of Neptune, revealing its true colors. A world far beyond our own, where the winds howl with ferocity and the skies tell tales of ancient ice and gas. What mysteries does this distant giant hold in its cerulean hues? Then we venture to the enigmatic Saturn, where atop its north pole, a geometric marvel, the hexagonal storm defies explanation. What forces of nature sculpt this bizarre phenomenon? Can we unlock the secrets of Saturn's hexagonal riddle? Our odyssey continues as we seek the latest real images of Uranus. This elusive ice giant, shrouded in mystery, reveals new truths through the eyes of modern exploration. What will we discover in the unseen details of its atmosphere and rings? Finally, we journey with Chandrayaan-3 to our celestial neighbor, the Moon. Here in the silence of the lunar surface, the mission uncovers sights unseen by human eyes. What did Chandrayaan-3 witness on the Moon? What secrets lie in the dust and craters of our closest companion in space? Join us as we traverse the cosmos seeking answers and marveling at the beauty of the universe. This is not just a journey through space, it's an exploration of the unknown, a quest for knowledge, and a tribute to the human spirit's unending curiosity. Welcome to our documentary series, where the mysteries of the universe unfold before your eyes. In the vastness of our solar system, beyond the belt of asteroids and gas giants, lies a world shrouded in mystery. Neptune, the 8th planet from our Sun, a distant ice giant, has long captured our imagination. For decades, we've imagined it as a dark blue sphere at the edge of our cosmic neighborhood. But what if the vision of this distant world was an elaborate illusion? This mysterious planet, named after the Roman god of the sea, has hidden its true colors from us. Cloaked in a shroud of deep blue, Neptune has been the subject of many stories and scientific investigations. But recent discoveries have removed this azure facade, revealing a reality far more complex and fascinating than we could have imagined. For years, our telescopes have been pointed at this distant giant, capturing its essence in pixels and data. What we saw, however, was not the reality of the planet, but a reflection of our own technological and perceptual limitations. The deep blue color we associated with Neptune was actually the result of our own interpretations and enhancements, a story we unwittingly created and believed. Today, we invite you to explore Neptune like never before. Delve into its true colors, understand its atmosphere, and unravel the secrets of its moons and rings. For centuries, Neptune was portrayed as a dark blue world whose color reflected its cold, distant nature in the solar system. This representation, deeply ingrained in our collective consciousness, has become the cornerstone of our understanding of this icy giant. But what if this image was a reflection of our perceptions rather than its true appearance? Neptune's color is a story of scientific evolution and the search for truth. It begins with the Voyager 2 probe launched by NASA in 1977. Sent to the outer reaches of the solar system, it took the first close-up images of Neptune, painting a picture of the planet awash in a stunning blue color. However, these images were not a direct window into the true color of Neptune. In fact, they were interpretations, the result of processing the data through the lens of human understanding and the technological capabilities of the time. The deep blue color we saw was the product of enhancements made by scientists to emphasize certain features of the planet. This story began to more advanced telescopes, such as the Hubble Space Telescope and the Very Large Telescope. These instruments, equipped with state-of-the-art technology, allowed astronomers to see the true color of the planet again. The results of this study were striking. The new images revealed that Neptune's color was not the previous deep blue, but rather a more muted and varied shade. This discovery was not just aesthetic, but a fundamental shift in our understanding of the planet. The reason for this color misconception lies in the way we process and interpret astronomical data. Colors in space images are often enhanced or altered to emphasize certain features or to make them more distinguishable to the human eye. In the case of Neptune, these enhancements over time have led to a collective opinion of its deep blue color. So, what led to this discovery? The key lies in a meticulous study entitled Modeling the Seasonal Cycle of Uranus's Color and Magnitude and Comparison with Neptune. This study, led by Patrick G.J. Irwin of Oxford University, along with a team of experts, set out to unravel the mysteries of Uranus's seasonal color changes. However, their journey will inadvertently shed light on the true colors of Neptune, disproving long-held beliefs. The team carefully analyzed a huge array of data obtained from Lowell Observatory over 6 decades. These data, supplemented by Hubble Space Telescope observations, produced a detailed picture of Uranus's disk-averaged color and photometric magnitude, revealing the complex interplay of its seasonal changes. One of the most important aspects of this study was the focus on the reflectivity of Uranus and the abundance of methane. The researchers unraveled a complex relationship between the lower methane content at polar latitudes and the different reflectivity of aerosol particles. This complex interaction of elements in the atmosphere of Uranus was thought to be influenced by the presence of methane ice particles, adding a new layer of complexity to our understanding. In parallel, the study allowed for a fascinating comparison with Neptune. Contrary to popular belief, the difference in blue hues between Neptune and Uranus was less pronounced. This discovery was the result of a critical reassessment of Neptune's color, disproving the image of deep blue that had been ingrained in our minds. The methodology used by the team was a combination of quantitative analysis, atmospheric modeling, and advanced spectroscopic observations. They converted measured reflectance spectra into radiance spectra, and then tri-stimulus values. This process mimicked the visible colors of the planets as perceived by the human eye, bridging the gap between the raw data and our visual interpretation. The use of advanced telescopes such as Hubble and the Very Large Telescope played an important role in this endeavor. These technological marvels allowed the team to revisit and re-examine the true colors of Uranus and, by extension, Neptune with unprecedented accuracy. As we delve deeper into the mysteries of Neptune, we find ourselves amid a maelstrom of atmospheric activity, in stark contrast to the relative calm of its stellar neighbor Uranus. Neptune's atmosphere, a turbulent and dynamic formation, is home to some of the most extreme weather in our solar system. One of the most striking features of Neptune's atmosphere is the presence of colossal storms, the most famous of which is the Big Dark Spot. Discovered by the Voyager 2 spacecraft in 1989, this massive storm, similar to Jupiter's Great Red Spot, is a testament to the turbulent nature of the planet. A large, dark spot, a giant rotating storm, is a window into Neptune's intense atmospheric dynamics. These storms are caused by the strongest winds in the solar system, reaching speeds of up to 1,300 miles per hour. However, to this day, the power and magnitude of these winds are a mystery to scientists, raising questions about their origin and the energy sources that drive them. In contrast, neighboring Uranus is a picture of tranquility. Its atmosphere, although composed of hydrogen, helium, and methane, does not have the same violent storms and extreme winds as Neptune. The difference in atmospheric activity between these two ice giants is one of the many mysteries of our solar system. Another intriguing aspect of Neptune's atmosphere is the presence of unusual hotspots, where temperatures can reach a staggering 750 degrees Kelvin. These hotspots represent a paradox because they exist on a planet so far from the Sun. The source of this heat remains a mystery, but theories suggest it could be caused by internal processes, such as auroras or magnetic reconnection in the plasma layers. The origin of these hotspots and the extreme weather conditions on Neptune are the subject of ongoing research. They force us to seek new answers to questions about planetary atmospheres and hint at complex internal processes that have yet to be understood. Stepping outside Neptune's turbulent atmosphere, we enter a realm of celestial harmony where moons and rings swirl around this icy giant. Turning our gaze to Triton, Neptune's largest and most intriguing moon, we discover a world of seasonal changes and atmospheric mysteries. Triton, a unique moon with a retrograde orbit, was the last solid object visited by the Voyager 2 spacecraft during its historic journey through the outer solar system. Because of its retrograde orbit, indicating that it was captured by Neptune's gravity, Triton stands out among the moons of our solar system. Its surface, covered in nitrogen ice, is geologically young and active, with dark green streaks indicating the presence of geysers spewing nitrogen gas. Triton's thin atmosphere, whose thickness varies with the seasons, is a fascinating study in extraterrestrial meteorology. Observations with the European Southern Observatory's Very Large Telescope have revealed that Triton's southern hemisphere is in the height of summer. This distant moon, despite its relative distance from the Sun, is experiencing significant atmospheric changes. The heat of the summer sun causes the thin layer of frozen nitrogen, methane, and carbon monoxide on Triton's surface to sublimate into gas. This process causes the icy atmosphere to thicken as the season continues in Neptune's 165 Earth-year orbit around the Sun. The season on Triton lasted more than 40 years, and the southern summer solstice occurred in 2000. The discovery of carbon monoxide in Triton's atmosphere, as well as the confirmation of the presence of methane, marked a significant advance in our understanding of this moon. The presence of these gases, especially the enrichment of ice with carbon monoxide in the upper surface layer, feeds the atmosphere and determines its seasonal dynamics. These findings required a revision of Triton's climate and atmospheric models. The complex interaction of nitrogen, methane, and carbon monoxide not only determines atmospheric conditions, but also provides insight into the geologic and climatic history of the moon. But Triton is not alone. The planet is accompanied by a retinue of smaller moons, each contributing to our understanding of this distant world. These moons also show seasonal changes and provide insight into the complex gravitational interactions and environmental conditions around Neptune. When we turn our gaze from the moons to Neptune's rings, we encounter another aspect of this planet's mysterious nature. Neptune's rings, made up of a mixture of dust and ice particles, are dull yet mesmerizing. They testify to the planet's dynamic history. Scientists believe they're remnants of moons that were destroyed by collisions or torn apart by Neptune's gravity. The composition and characteristics of these rings are closely related to Neptune's true color and atmospheric phenomena. The subtle hue of the rings, which were affected by light scattering in Neptune's atmosphere, add another layer to the planet's color palette. The rings, reflecting and refracting light from the Sun, create the overall appearance of Neptune seen from afar. In 2022, the James Webb Telescope captured the clearest view of the rings of this distant planet in 30 years. Photographed with unprecedented clarity, these rings have changed the way we think about this distant planet. The most striking thing about the new Webb image is the clear view of Neptune's rings. Some of these rings, dim and dusty, have not been detected since the historic Voyager 2 flyby in 1989. The Webb telescope, with its enhanced capabilities, has brought these elusive rings back into focus. Neptune's rings are made up of several bright and narrow, as well as fainter dust bands. Infrared imaging by the Webb telescope has put these rings in a new light, revealing features that were previously hidden in the darkness of space. This is the first time these rings have been seen in the infrared spectrum, providing new insights into their composition and behavior. Neptune's rings, like the planet itself, are characterized by a unique composition. Unlike the gas giants Jupiter and Saturn, Neptune is an ice giant, rich in elements heavier than hydrogen and helium. This composition also reflected in the planet's signature blue color in visible wavelengths caused by a small amount of methane gas. In infrared images taken by Webb's NIRCam, near-infrared camera, Neptune does not appear blue, in contrast to the darkened appearance one would expect due to methane absorption of light. In infrared images taken by the Space Telescope, Neptune appears as a luminous, glowing white sphere. This absorption also affects the appearance of Neptune's rings, as they reflect and refract light traveling through the planet's atmosphere. This unexpected brightness in the infrared is the result of a unique interaction between the planet's atmosphere and infrared light. While methane gas absorbs red and infrared light, high-altitude clouds in Neptune's atmosphere reflect sunlight before it's absorbed. These methane ice clouds appear as bright streaks and spots that cast a ghostly glow on the planet in the infrared spectrum. By the way, you may wonder why Triton looks like a dazzling point of light adorned with shining spikes, as opposed to the more subdued image of Neptune. These diffraction spike patterns are a characteristic feature of the imaging telescope. They're not physical structures, but rather optical artifacts created by the telescope's design. Light from Triton passing through the mirrors and telescope structure is diffracted, resulting in these striking peaks emitted by the moon. Diffraction, in simple terms, is what happens when a wave, such as light, travels around the edge of an object or through a small opening. Imagine light in the form of water waves flowing through a narrow slit in a wall. When the waves pass through the slit, they diverge in different directions, instead of just going straight through. This propagation of waves after passing through a hole or around an edge is what we call diffraction. In the context of the James Webb Space Telescope and its images, diffraction peaks arise because of the way the mirrors and structure of the telescope are arranged. When light from a bright object, such as a star or Triton in images of Neptune, enters the telescope, it's bent slightly by the edges of the mirrors and other parts of the telescope. As a result of this bending, the light diverges and forms the star-like spikes we see in the images. The study of Neptune's rings, especially in the infrared, provides valuable insights into the atmospheric conditions and internal composition of the planet. The interaction of the rings with Neptune's atmosphere, particularly the methane ice clouds, provides insights into the planet's climatic and environmental processes. The bright equatorial band that girdles the planet hints at the global atmospheric circulation, a key driver of the planet's winds and storms. The atmosphere, which sinks and warms near the equator, glows more intensely in the infrared than the cooler gases that surround it. As we conclude our journey through the mysterious world of Neptune, we reflect on the impact these discoveries are having on the broader field of planetary science and exoplanet exploration. Neptune, once a distant blue spot, is now a testament to space exploration's dynamic and ever-evolving nature. Discoveries concerning Neptune's true color, its atmospheric phenomena, and the intricate details of its rings and moons go far beyond our solar system. They provide a crucial example for understanding similar ice giants and exoplanets in the far reaches of our galaxy. The insights gained from Neptune will help astronomers decipher the mysteries of these distant worlds and enrich our knowledge of the universe. As we continue to gaze into the cosmos, Neptune reminds us of the limitless potential for discovery. Its example encourages us to keep looking, asking questions, and unraveling the mysteries of the universe. Saturn has captivated the human imagination. From ancient civilizations to modern astronomers, the Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. How? The mystery deepens. Saturn has long been a symbol of the unknown and mysterious. Its iconic rings have been the subject of wonder and speculation since the time of Galileo. But what if we told you that these rings, however eternal they may seem, are actually a fleeting cosmic phenomenon? Adding to the intrigue is a storm twice the width of Earth, with a mysterious hexagonal shape that's raging at Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries don't end there. Saturn's satellites, Titan and Enceladus, offer conditions that could potentially support life. Lakes of liquid methane and geysers spewing water and organic material into space make these satellites more than just celestial bodies. They're potential homes for life. Join us for a closer look at this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who first pointed his telescope at Saturn in 1610. What he saw puzzled him, a planet with something like ears. He didn't realize he was looking at the edges of Saturn's magnificent rings, a feature that would puzzle astronomers for centuries to come. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 that Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. Moving into the modern era, we witnessed the Pioneer 11 mission, the first spacecraft to fly past Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were once inaccessible to Earth's telescopes and us. But it was the Cassini mission that truly revealed Saturn in all its glory. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings, and its satellites. From discovering plumes of water ice on Enceladus to capturing the ethereal beauty of a hexagonal-shaped storm at Saturn's North Pole, Cassini revolutionized our understanding of this distant world. And here's an interesting point. Long before the advent of telescopes, the Maori people of New Zealand had myths that described Saturn as having a pareo, or belt, around it. How they knew this remains a matter of debate and speculation. But as we'll see later, Saturn holds more than one mystery. What do you think could have created a hexagonal storm with an area larger than the Earth itself? Saturn harbors a geometric enigma at its North Pole, a six-sided storm that's puzzled scientists for decades. This six-sided wonder is not just a superficial feature, but a deep and enduring mystery that breaks down the understanding of fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft. But it wasn't until the Cassini mission, which orbited Saturn from 2004 to 2017, that we got a front-row seat to this cosmic spectacle. Cassini's high-resolution images showed a symmetrical jet stream surrounding the hurricane-like vortex at the center of the hexagon. Unlike Earth's chaotic weather systems, Saturn's hexagon is a masterpiece of geometric precision. So what's causing this hexagonal storm? Researchers at Harvard University have developed a 3D model that suggests deep thermal convection in Saturn's outer layers may be the culprit. This model shows that the storm could spread thousands of kilometers deep into Saturn's atmosphere, well beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in a laboratory setting. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they provide a glimpse of extraterrestrial phenomena. Saturn's hexagonal vortex contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of the gas giants from the Earth group planets. The longevity of the hexagon is another mystery. It's been observed for at least 4 decades, and possibly much longer. This steady feature suggests that everything that feeds the hexagon is not a temporary phenomenon, but a stable, perhaps even permanent, aspect of Saturn's internal dynamics. Let's shift our attention from the mystery of the hexagon to another wonder of Saturn. Saturn's rings are more than just celestial jewelry. They're dynamic, ever-changing systems that interest astronomers and the public alike. But what are these rings made of, and why are they so short-lived? Saturn's rings are composed mostly of water ice with a mixture of dust and rocky material. They range in size from tiny particles to huge chunks the size of houses. These ice particles are not static. They're in constant motion under the influence of Saturn's gravity and the gravitational pull of its satellites. The rings are divided into several subdivisions and gaps, each with its own unique characteristics. Most notable are the A, B, and C rings, separated by gaps, such as the Cassini ring, a gap 3,000 miles between the A and B rings. The origin of Saturn's rings has been the subject of debate. One popular theory suggests that they formed from the remnants of a shattered moon. Another theory states that they're the remnants of material from the formation of the solar system, captured by Saturn's gravitational pull. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on the rate of dust contamination. Saturn's rings don't last forever. They're slowly disappearing because of a phenomenon known as ring rain, in which ring particles are drawn into Saturn's atmosphere. This process is accelerated by micrometeoroid bombardment and interaction with Saturn's magnetic field. At the current rate, some scientists predict that Saturn's rings could disappear within 100 million years. The depletion of the rings would not only change Saturn's appearance, but could also have consequences for its atmosphere and magnetic field. As we pause for a moment, we realize that even the most fascinating features of our universe are not immune to the inexorable forces of physics doomed to disappear into the chronicle of eternity. Saturn, the ringed giant of our solar system, is not just a celestial wonder. It's also a cosmic playground that contains some of the most intriguing satellites, 2 of which, Titan and Enceladus, have fascinated scientists and sparked debate about the potential for life beyond Earth. Titan, Saturn's largest satellite, is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what's truly amazing is Titan's rate of removal from Saturn, 100 times faster than previously thought, amounting to a staggering 4.3 inches per year. This rapid drift suggests a dynamic and evolving relationship between Titan and Saturn. Could this drift affect Titan's internal dynamics? And perhaps even its potential for the existence of life. An atmosphere rich in organic compounds such as nitrogen and methane, and the possibility of an underground ocean, make Titan a tempting target for the search for extraterrestrial life. But the question remains, what would life look like in an environment so radically different from Earth's? And let's remember Enceladus, another satellite of Saturn that's very different from Titan. It's an icy world with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the concept of an ocean world to a new level. Not only does it have a subsurface ocean, but it also sprays it into space, where samples of it can be collected by a space probe. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water erupting from hydrothermal vents. Hydrothermal vents can provide the necessary conditions for life as we know it. On Earth, these vents are teeming with life forms that thrive in extreme conditions. Could Enceladus's vents be home to similar but alien life forms? Enceladus also contributes to Saturn's E-ring, a unique characteristic that further enriches the dynamic relationship between the Moon and its host planet. The icy particles in this ring open a window into the Moon's internal chemistry, providing clues that may reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but quite different in their characteristics. Both present compelling arguments in favor of the potential for life, fueling our curiosity. As we ponder the possibilities of life on Saturn's satellites, it's worth noting that our curiosity is not limited to telescopes and computer modeling. Upcoming missions aim to study these satellites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan. Scheduled for launch in the 2030s, this rotorcraft will fly over Titan's diverse terrain, from dunes to impact craters. Dragonfly's main goal is to search for the building blocks of life. It will analyze complex organic compounds in the atmosphere and on the surface, providing invaluable data on Titan's chemistry. Equipped with a suite of scientific instruments, Dragonfly seeks to understand the geologic processes on the Moon and how they relate to its potential for life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although no missions to Enceladus are currently planned, the Moon's potential for life has made it a prime candidate for future exploration. Scientists are proposing missions that could fly through Enceladus's plumes and directly sample its underground ocean. Such a mission could analyze the chemistry of the plumes in search of signs of life or prebiotic chemistry. The presence of hydrothermal vents in Enceladus's oceans adds another layer of intrigue, suggesting an environment in which life could potentially thrive. Despite the technical challenges, a mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence for the existence of extraterrestrial life, or at least provide clues to the conditions necessary for life to exist. As we mentioned, Saturn's rings don't last forever, as we once thought. Recent studies have shown that a process that can last hundreds of millions of years is causing these icy wonders to slowly fade away. But what significance does this have for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, composed mostly of water, causes a decrease in electron density in Saturn's atmosphere. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. Ring rain is not just a trickle. It's a stream that carries away water in amounts equivalent to an Olympic-sized swimming pool every half hour. Compounding the mystery is the relative youth of Saturn's rings. Although Saturn itself is about 4.6 billion years old, data from NASA's Cassini mission suggests that the rings may be only a few 100 million years old. This leads us to wonder, if Saturn's rings are so young, what catastrophic event could have led to their formation? Was it the destruction of a moon? Or perhaps the capture of a passing comet? Cassini's Space Dust Analyzer has added another layer of complexity. Over 13 years, it's collected 163 dust particles that came from outside the Saturn system. Surprisingly, the rings turned out to be quite clean, suggesting that they hadn't existed long enough to accumulate excess cosmic dust. This cleanliness raises the question, if the rings are young, why haven't they collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age. and their interaction with the wider cosmic environment. It's as if the rings are in a cosmic laboratory room or clean room, isolated from the dust that permeates the rest of the solar system. As the rings are depleted, Saturn's appearance will undergo a dramatic transformation. These rings have been the planet's hallmark. Their disappearance would not only change Saturn's appearance, but could also have unknown consequences for its atmosphere, perhaps even affecting the planet's albedo and heat retention. The loss of the rings could have a cascading effect on Saturn's atmosphere, potentially altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making them a subject of intense scientific interest. Interestingly, the fate of Saturn's rings may be inextricably linked to its satellites. Some theories suggest that gravitational instability may have destroyed some of the icy satellites orbiting Saturn, providing enough material to form the rings. Saturn's rings and satellites are like partners in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can say unequivocally that the fate of one can shed light on the mysteries of the other. In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but holds secrets that may unravel some of the most enduring mysteries of the cosmos. Far beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It's a world that lives at a different rhythm, spinning on its side, an oddity that's long puzzled astronomers and spawned countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, extending the known boundaries of our solar system. For centuries, this distant world was just a speck of light in our telescopes, a ghostly blue ball, distant and aloof, keeping its secrets. But now, with the advent of the James Webb Space Telescope, a new chapter in the exploration of Uranus is opening. JWST, with its unprecedented vision, peels back the layers of this icy giant, revealing a world of amazing beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In the quest to understand the universe, humankind has launched a Sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This Sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, the successor to the legendary Hubble Space Telescope. Equipped with a set of advanced instruments and a mirror more than 6.5 meters in diameter, JWST is designed to observe the universe in light invisible to the human eye, the infrared spectrum. This allows the telescope to peer through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was a feat in itself. Launched on an Ariane 5 rocket, JWST traveled to a point in space known as the Second Lagrange Point, or L2, 1 million miles from Earth. Here, in this stable orbit, JWST can observe the universe with minimal interference from Earth and the Sun. JWST's capabilities are not limited to observing the early universe or distant galaxies. It plays a key role in unlocking the mysteries of our solar system. Its powerful instruments, such as the Near-Infrared Camera, NIRCam, and the Mid-Infrared Instrument, MIRI, reveal new details about planets, moons, and other celestial bodies closer to home. Take Uranus, for example. In the past, our view of this distant planet was limited to faint images from telescopes such as Hubble. But now, thanks to JWST's enhanced infrared capabilities, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe the planet's atmosphere, weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light of Uranus, JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations, revealing more details about our universe every day. Its latest triumph is a series of images of Uranus taken very recently, surpassing even the stunning observations made in April 2023. In early 2023, JWST provided us with unprecedented views of Uranus, allowing us to look at the planet's atmospheric dynamics and ring system in a new light. The recent images, however, are a step further. Not only are they clear, they reveal aspects of Uranus that were previously hidden or obscured, even in April observations. Take the rings of Uranus, for example. The latest images show them with even greater clarity. We can now observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of JWST lies not only in its one-off observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are particularly striking. Bright white caps and dark bands near the poles, the origin of which is still unclear, have shown marked changes. This continuous observation provides invaluable data for understanding the seasonal changes and long-term climate patterns of Uranus. In the set of planets in our solar system, Uranus stands out with a peculiar feature, an extraordinary axial tilt. Unlike any other planet, Uranus rotates practically on its side, tilted at an angle of about 98 degrees. This unique orientation has long intrigued astronomers and sparked a quest to understand its origin and consequences. To understand the significance of this tilt, we must travel back in time to the early days of our solar system. Uranus probably formed with a much less severe tilt. The prevailing theory suggests that a catastrophic event, perhaps a collision with a planet-sized object, dramatically changed its orientation. This colossal impact would have thrown Uranus aside, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme tilt results in extreme seasons, unlike those observed on other planets. The implications for planetary observations and research are enormous. Uranus's tilt allows us to observe its rings and satellites from different perspectives, offering insights into their composition and dynamics. For example, when Uranus's rings face the Earth, they become nearly invisible, exposing fainter dust bands and smaller satellites. Compare that to Earth, which is tilted only 23.5 degrees. Uranus's extreme tilt causes drastic changes in its weather patterns, which is a goldmine for scientists studying planetary climate. Tilt also affects the circulation of Uranus's atmosphere. Prolonged exposure to sunlight at the poles can result in complex weather systems, as seen in recent JWST images. These systems are very different from those on other planets and provide a unique laboratory for understanding atmospheric physics. Let's take a journey on one Uranian year. Each season on Uranus lasts about 21 Earth years, a consequence of its 84-year orbit around the Sun. This extended duration means that each hemisphere experiences long periods of daylight, followed by equally long nights. As a result, the planet undergoes dramatic changes in appearance and climate. Because one pole of Uranus basks in uninterrupted sunlight, summers are long, while the opposite pole plunges into a deep, dark winter. This stark contrast creates unique atmospheric conditions, causing complex weather patterns and climatic shifts. The impact of these seasonal changes on Uranus's atmosphere is profound. When the sun illuminates the planet's surface, it warms the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static. They evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking features are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. Conversely, dark storm patches that look like giant hurricanes roam the planet's surface. Moreover, the planet's seasonal phenomena affect not only the planet itself, but also its moons. One recent study of Uranus's moons, or rather a phenomenon that's particularly intriguing, is the development of temporary atmospheres on these moons, a spectacle caused by the unique conditions of the Uranus system. The key to understanding these temporary atmospheres lies in the extreme tilt of Uranus's axis and its effect on the satellite's orbits. As these satellites orbit the planet, they experience dramatic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During the long summer exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to a gas, bypassing the liquid phase. This sublimation creates thin, temporary atmospheres, or exospheres, that envelop the satellites. These exospheres are most pronounced when moons are warmest. Recent research by the James Webb Space Telescope shows that this phenomena is more dynamic and complex than previously thought. Exospheres are heterogeneous. They vary in composition and density, depending on the topography of the moons and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. Gases recondense on the surface, returning to an icy state. This cycle of atmosphere creation and disappearance is a unique characteristic of Uranus's satellites, opening a window into the interaction between solar radiation and surface ice. The rings of Uranus, often overshadowed by the majestic rings of Saturn, hold their own tale of cosmic intrigue and dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known but no less fascinating celestial features. In contrast to the wide and bright rings of Saturn, the rings of Uranus are narrow, dim, and less extensive, extending to 4 planetary radii. This includes elusive rings, such as the Mu and Nu rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of Uranus's 5 major satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and masses relative to Uranus provide a better understanding of the formation of the satellites and the gravitational formation of the rings. The formation of Uranus's rings is attributed to a combination of processes, including collisions, satellite breakup, and gas release from the main satellites. These dynamical processes affect the material composition of the rings and are influenced by the ever-changing environment of the Uranus system. The stability of the rings is intrinsically linked to their dynamical interactions with the satellites of Uranus. The study examines how accretionary processes occur within the Roche limit and how the dynamics of shepherding moons play a crucial role in maintaining the rings. In addition, the rings provide a unique opportunity to understand the internal structure of Uranus through seismological studies. Modeling results show how these satellites shape the ring system, affecting its structure and stability over time. The modeling predicts significant material loss within the ring system, primarily due to gravitational interaction with the satellites. The complex dance between moons and rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the material distribution of the rings are crucial to understanding the structure and the evolution of the rings. The study also examines the role of satellite-to-satellite interactions in the evolution of the system, especially past resonances between satellites such as Ariel and Umbriel, and their impact on the orbits and geology of satellites, especially Miranda. But the mysteries surrounding this planet don't end there. You've probably heard of the Aurora Borealis. Well, the latest discovery concerns the auroras of Uranus, which also has them. However, its auroras, unlike Earth's, occur in the infrared spectrum. Using the Keck 2 telescope, astronomers observed enhanced emissions of trihydrogen cation in the planet's atmosphere. This is a groundbreaking discovery that sheds light on the unique magnetic field and dynamics of Uranus's atmosphere. Uranus's magnetic field, which is significantly deflected from the planet's axis of rotation, creates a unique coupling of the magnetosphere, ionosphere, and thermosphere. The detection of these infrared auroras is crucial because it opens up a new window into these processes, previously elusive due to the lack of such detections on Uranus. Comparing the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where the H3+ emissions have short lifetimes that smooth out the variability of the UV emission, the brightest infrared emissions of Uranus do not necessarily coincide with the brightest UV emissions of the other planets. This unique aspect of Uranus's polar lights provides valuable information for exoplanet studies, especially for the worlds of warm ice giants. The study delves deeper into the unusual heat spots on Uranus observed near the latitudes of the UV northern lights. These spots, analyzed for temperature, column density, and total emission, suggest that the enhancement is not caused by temperature, but rather by increased ionization, probably due to polar aurora activity. Polar lights play a significant role in heating the atmosphere, and on Uranus, the increased H3+ emissions associated with these auroras suggest their involvement in atmospheric processes. By studying such unique things, we gain a deeper understanding of similar processes in different planetary environments, enriching our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas beckoning closer exploration. Recent research, including a fresh analysis of Voyager images, has revealed that the two planets actually have similar shades of greenish-blue color, fundamentally changing our long-held beliefs. Uranus and Neptune share many common characteristics. They're roughly the same size, have the same mass, and are surrounded by deep atmospheres of comparable materials. Nevertheless, it was long thought that their appearance was quite different. This misconception has now been corrected. Both planets are shown in their true colors, largely influenced by the methane layer in their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar icy giants. The mission's potential goals range from studying the unique magnetic field and complex ring system to investigating atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the Uranus Orbiter and Probe mission has been elevated to the highest priority for NASA flagship mission within the 2023-2032 Planetary Science Decadal Survey. Future launch windows are available between 2030 and 2034. Key science goals will include a detailed analysis of the unusual tilt of Uranus's axis and its effect on the planet's climate and weather patterns. The mission can also study the intriguing phenomena of infrared auroras and their role in heating the atmosphere, providing a comparative study with other planets. Studying Uranus and Neptune will also provide valuable information about planetary evolution and dynamics. Understanding why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, allowing methane haze to accumulate, can tell us a lot about atmospheric processes on the ice giants. As we await a future mission to Uranus, we stand on the threshold of discoveries that could redefine our understanding of the outer solar system. Exploring this distant ice giant will not only unravel its mysteries, but will also expand our knowledge of planetology as a whole, shedding light on the complex picture of our cosmic home. The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folkloric tales, the moon holds secrets that have eluded us for centuries. Among these mysterious features is the moon's south pole, a region shrouded in perpetual shadow and intense cold, untouched and unexplored by any previous lunar mission. This is the story of Chandrayaan-3, India's daring journey into uncharted territory. Launched on a journey of more than 238,600 miles, Chandrayaan-3 embarked on a mission not just of distance, but of discovery. Its purpose? To unravel the mysteries of the moon's south pole, a place where sunlight barely reaches, an area where the terrain is so treacherous that you have to wade through an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 sought answers to questions that have puzzled scientists for decades. What lies beneath the surface of this mysterious region? Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here in the form of ice. When Chandrayaan-3 ventured beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. Its primary goal was clear, yet challenging: to achieve a soft landing near the moon's south pole, a feat that had never before been accomplished. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists and engineers piloted this ambitious mission. Their expertise helped Chandrayaan-3 traverse the space void, overcoming the challenges of lunar orbit insertion and descent. The south pole of the moon is a landscape unlike any other. Here, the terrain is a patchwork of craters and mountains, many of which are shrouded in perpetual darkness. The challenge was not just to land, but to land safely in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram landing module separated from the orbiter, it began its descent. The landing module, equipped with advanced sensors and engines, began its perilous journey to the surface of the moon. Imagine a spaceship autonomously navigating a maze of craters and boulders in search of a patch of land safe enough to land on. The landing module's onboard systems were hard at work, analyzing every inch of the terrain below. Against this treacherous landscape, the landing module also struggled with extreme temperatures. The moon's south pole is a place of stark contrasts. The sun barely rises above the horizon, while shadows hide frigid temperatures that can drop to minus 382 degrees Fahrenheit. As the landing module made its final approach, the hearts in the Flight Control Center beat harder. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a light thud, Vikram landed, marking an historic moment not only for India, but for lunar exploration in general. In the silence of the moon's south pole, Chandrayaan-3 began its mission of exploration and discovery. So, after the historic landing of Chandrayaan-3, a new chapter in lunar exploration began. The mission's goal was to maximize the study of the moon's characteristics, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just beneath its surface. The lunar exosphere, the thin layer of gases surrounding the moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, the moon's exosphere is so rarefied that it almost resembles a vacuum. The Chandrayaan-3 instruments, developed using the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delved deeper into the moon's ionosphere. This layer, formed by solar energy ionizing atoms in the exosphere, plays a crucial role concerning lunar communication and navigation. The Chandrayaan-3 measurements were designed to provide unprecedented information on the density and behavior of the ionosphere, which is important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was studying the temperature variations just beneath the lunar surface using one of 4 instruments on the landing module, CHASTE, or Chandra's Surface Thermophysical Experiment. The temperature probe, immersed in the lunar regolith, was tasked with the critical mission of mapping the thermal profile of the lunar soil. The results of Chandrayaan-3 revealed a sharp contrast in temperatures. On the surface, during a lunar day, temperatures rose dramatically to 140 degrees Fahrenheit. While just 8 centimeters deeper, they dropped significantly to 14 degrees Fahrenheit, demonstrating the lunar soil as a potential thermal insulator. This discovery provided new opportunities for future lunar habitats, suggesting that the lunar regolith could serve as a thermal insulator, protecting astronauts from the moon's harsh extreme temperatures and harmful radiation. These studies were more than just scientific endeavors. They were stepping stones toward a future in which the moon could be a gateway to future space exploration. Mission results on the lunar exosphere, ionosphere, and subsurface temperature laid the foundation for understanding the moon's environment and its potential to support human life. Standing in the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon that had not been observed for more than 50 years, a lunar earthquake. The mission succeeded in shedding light on one of the most intriguing and least understood aspects of the moon. The Instrument for Lunar Seismic Activity, or ILSA, a seismic instrument, was designed to detect the slightest tremors on the moon, and it did. Chandrayaan-3 detected what looked like a lunar earthquake, a significant discovery given that the last such observation was made during the Apollo missions in the early 1970s. Lunar quakes are fundamentally different from earthquakes. While Earth's seismic activity is largely due to the movement of tectonic plates, the Moon, which is devoid of these plates, experiences earthquakes for a variety of reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a subject of scientific interest. The Chandrayaan-3 data suggests several possible causes for these earthquakes. One theory is a collision with meteoroids, which could cause shock waves that penetrate the Moon's crust. Another is Earth's gravitational pull, causing tidal forces that load the lunar crust. And finally, extreme temperature fluctuations on the Moon's surface can cause expansion and contraction, leading to earthquakes. These earthquakes are not just surface phenomena, they're windows into the Moon's interior. By analyzing the seismic waves, scientists can infer the composition and structure of our satellite's interior, which resembles a sonogram of the lunar interior. Such information is of great importance for understanding the formation and evolution of the Moon. The detection of a lunar earthquake by the Chandrayaan-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened up new insights into the geological processes that shape the Moon. To unravel the geologic mysteries of the Moon, Chandrayaan-3 carried out another exploration. Among the most intriguing finds was the discovery of sulfur, an element whose presence on the Moon has been shrouded in mystery. The Laser-Induced Breakdown Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes tiny samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thereby revealing the presence of various elements, including sulfur. Sulfur on the Moon is a significant find. On Earth, sulfur is often associated with volcanic activity, raising questions about similar processes on the Moon in the past. Its presence could provide insight into the volcanic history of the Moon and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrayaan-3 was the search for water ice, a search that's intrigued scientists for decades. Water ice on the Moon is not just a scientific curiosity, it's a potential resource for future human missions, offering water for life support and fuel production. Despite high hopes, Chandrayaan-3, like its predecessors, found no direct evidence of water ice on the Moon's surface. However, the lack of direct evidence is not a conclusion, but a clue leading to new hypotheses. One theory is cold trapping, in which water vapor can migrate to permanently shadowed craters of the poles, freezing into ice. The detection of sulfur adds another layer to this theory, as sulfur may be trapped with the water ice and released as a result of the breakdown of water molecules by high-energy solar radiation. The lack of direct evidence for the existence of water ice raises important questions. Is the ice deeper beneath the surface, shielded from detection by the insulating properties of the lunar soil? Or is its prevalence more heterogeneous and elusive than previously thought? During its exploration of the Moon's south pole, Chandrayaan-3 found more than just sulfur. The rover's LIBS instrument made the first ever in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each element reflecting part of the complex geologic history of the lunar surface. Further measurements added new details to this discovery, further revealing the presence of manganese, silicon, and oxygen. These elements, each with its own unique spectral signature, provided clues to the formation of the Moon and its evolutionary history. Studies of the presence of hydrogen, a key component in the search for water, also continue. The mission's discovery of these elements and the ongoing search for water ice underscore the dynamic and complex nature of the Moon's geology. Each discovery, each unanswered question, moves us further in our quest to understand our nearest celestial neighbor and prepares us for the next steps in lunar exploration. As the Chandrayaan-3 mission at the Moon's south pole opened a new chapter in lunar exploration, it also paved the way for the next ambitious leap, the Lunar Polar Exploration Mission, LUPEX for short. This joint venture between the Indian Space Research Organization and Japan Aerospace Exploration Agency is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the South Pole region of the Moon. JAXA will likely provide the H-3 launch vehicle and rover under development, and ISRO will provide the lander. This mission represents a significant step in international cooperation on lunar exploration. The mission's goals are multifaceted. It will demonstrate new surface exploration technologies critical for sustained lunar exploration in the polar regions. Precise landings will be achieved by using a feature-matching algorithm and navigation equipment derived from the JAXA Smart Lander for Investigating Moon mission. The LUPEX rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples from a depth of 5 feet, 1.5 meters. Finding and analyzing water are key goals of the mission, and the potential discovery of water ice could be a game-changer for future lunar missions. In parallel with LUPEX, ISRO's Chandrayaan-4 mission, designed to return samples from the Moon, is in the planning stage. Scheduled for launch by 2028, Chandrayaan-4 will consist of 4 modules. a transition module, a descent module, an ascent module, and a re-entry module. The ambitious goal of the planned mission is to return soil samples from the Moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, including sample collection, docking in lunar orbit, and returning samples to Earth. Chandrayaan-3's innovative discoveries, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the Moon's mysterious nature. These results provide crucial insight into the Moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration is promising. Missions like LUPEX and Chandrayaan-4, building on the legacy of the previous ones, will continue to explore the mysteries of the Moon. India's role in these endeavors is not only that of a participant, but also that of a pioneer. Such events truly inspire us to look beyond the boundless mysteries of the cosmos. There are countless untold stories in the universe, but one mystery veiled in the shadows of distant suns stands out prominently among many others. This discovery invites us to look beyond earthly boundaries and ponder untold possibilities. This is the story of Kepler-22b, a planet that's not just wandering in the void, but basking in the sweet spot, its star's habitable zone. Here, in this delicate balance, all conditions exist to ignite the magic of life, for the water to flow freely and the atmosphere to hold the secrets of existence. Discovered by the gaze of the Kepler Space Telescope, Kepler-22b invites us to ponder what worlds may lie beyond our own, to question our understanding of life and our role in the universe. It makes us dream of new horizons, of distant shores where humanity may one day set foot. Today we'll embark on a journey of discovery to unravel the mysteries of Kepler-22b and the countless other worlds that await us beyond our reach in the limitless expanse of space. In its search for Earth analogs scattered throughout the galaxy, the Kepler Space Telescope has become a pioneer, a celestial cartographer mapping the unknown. Initially, Kepler's mission was very clear: to observe the vastness of the Milky Way, looking for the faint twinkle of stars dimmed by the passing of planets in their orbit. Equipped with the most sensitive photometers, the telescope patiently watched the light of more than 150,000 stars. Among them, a pattern emerged: the rhythmic fadings of a particular star, not unlike our Sun. This was the first hint of Kepler-22b, a planet moving carefully around its star and briefly eclipsing its light, as if playing cosmic hide-and-seek. This discovery was a real event. The analytical skill required to sift through huge datasets and pick out planetary transits from the cacophony of cosmic noise was immense. It was akin to detecting a faint brightness difference caused by a moth flying in front of a lighthouse beam from thousands of miles away. The method of transits, Kepler's main tool, is a deceptively simple but very powerful technique. This method is based on the subtle interactions of planets orbiting their stars, passing in front of them for a moment and casting a small shadow, which then causes a slight dimming of the star's light. It's this faint, fleeting shadow that astronomers look for, a sure sign of a distant world orbiting its star. The elegance of the transit method lies in its simplicity and the wealth of information it provides. When a planet passes in front of its star, it blocks some of the starlight, causing a measurable dip in brightness. This dip, detected by instruments such as the Kepler photometer, is carefully analyzed to reveal not only the presence of the planet, but also its size. The amount of obscured light tells us how large a planet is compared to its star. Moreover, the regularity of these brightness variations reveals the planet's orbital period, the time it takes to complete one orbit around its star. This rhythm of disappearance and reappearance allows scientists to calculate how far away a planet is from its star, which provides crucial information about the planet's environment and its probability of habitation. This method also opens a window into the planet's atmosphere. When a star's light passes through a planet's atmosphere during transit, certain wavelengths of light are absorbed by atmospheric gases. By studying these changes in the star's spectrum, astronomers can determine the chemical composition of the planet's atmosphere, finding fingerprints of molecules that may indicate the presence of water, oxygen, or even signs of biological activity. The discovery of Kepler-22b was a watershed moment in the search for Earth analogs. It highlighted the incredible potential of our technology and the perseverance of scientists. This discovery has moved us further along the path of space exploration, opening new chapters in the history of the search for worlds that could one day become a second home for humanity. In the variety of cosmic interactions between planets and stars, there is a delicate region, a narrow band where conditions are just perfect, where the hope of life as we know it lingers in the darkness. This region, known as the habitable zone, is a cradle for potential life. A haven where water can exist in a liquid state, neither boiling under the fierce light of a star, nor freezing in the cold expanse of space. Imagine a world very similar to our Earth, located inside this life-supporting belt. Here, the heat from the star is neither too intense nor too weak, bathing the planet in soft light. And this is where Kepler-22b is, orbiting serenely in the habitable zone of its star, a prime candidate in the search for Earth-like conditions and possibly life beyond our solar system. Just as Earth thrives in the Sun's habitable zone, Kepler-22b enjoys a similar privilege, orbiting at a distance where temperatures can allow lakes, rivers, and oceans to exist. The presence of liquid water, the universal solvent of many chemicals, is crucial, for it is in water that the chemistry of life unfolds. Water is the stage on which the drama of life is played out, from the simplest bacteria to the most complex forms of flora and fauna. Yet only the presence of water in a liquid state is one of the many conditions necessary to sustain life. What have we learned from analyzing this distant world? And is it so open to the theoretical presence of humans on it? As we dive into the mysteries of Kepler-22b, we embark on a journey of discovery, piecing together the puzzle of this distant world through the lens of our own Earth. With each observation, scientists are getting closer to understanding the fundamental nature of this distant planet, its size, its composition, and the very air that surrounds it. It's these factors that will help shed light on the presence of the basic components that may make this distant world a cradle for life. So, what are these factors? At the forefront of the search for life is, of course, the presence of liquid water, the cornerstone for all known biological processes on Earth. As we already know, Kepler-22b, which occupies a privileged position in the habitable zone, receives from its star a flow of energy that suggests that the temperature may be favorable for maintaining water in a liquid state. While the presence of liquid water is a promising start, the composition and behavior of Kepler-22b's atmosphere remains crucially unknown. Enveloping the planet, the atmosphere is the most important determinant of environmental conditions affecting temperature and surface pressure. Because the planet is in the habitable zone of its star, the theoretical presence of an atmosphere similar in composition to Earth's, rich in nitrogen and containing the requisite amount of oxygen and trace gases, could mean a temperate climate and stable water cycles similar to those that have nourished life on our home planet for billions of years. However, the range of possible atmospheric scenarios is enormous and shrouded in uncertainty due to our current technological limitations in directly observing exoplanet atmospheres at such great distances. If Kepler-22b's atmosphere tends toward a denser, carbon dioxide-dominated composition like that of Venus, this could lead to a greenhouse effect. In such a scenario, any potential water would exist as supercritical vapor at extreme pressures and temperatures. Conversely, an atmosphere that's too thin and free of greenhouse gases could turn Kepler-22b into a frigid world where water exists only as ice, and the surface is exposed to harmful cosmic radiation. The equilibrium temperature of the planet, estimated at a comfortable 72 degrees Fahrenheit under Earth-like atmospheric conditions, indicates the possibility of an environment with ideal conditions for Earth-like life. However, if one were to go to the other extreme and create a Venus-like greenhouse effect, the surface temperature could soar to a scorching 860 degrees Fahrenheit, which would likely preclude the existence of life as we know it. Things get even more complicated. The elemental recipe for life goes beyond just water and the right atmosphere. Life, as we know it, is intricately woven from a variety of chemical elements, with carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur playing major roles. Sun-like stars, including Kepler-22, are G-type stars and typically have similar proportions of hydrogen and helium, with a small amount of heavier elements playing a primary role. However, during planetary system formation, the distribution and concentration of materials in the protoplanetary disk around the nascent star influence the further composition of the forming planets. Temperature gradients in this disk lead to condensation of different materials at different distances from the star, which affects the composition of the planets. Once a planet is formed, its composition can be altered by differentiation, the separation of different materials within the planet, resulting in the formation of distinct layers, such as the core, mantle, and crust, and geologic processes such as volcanic activity and plate tectonics. So while direct measurements of the chemical composition of Kepler-22b are beyond our capabilities, the diversity of elements in the universe and the planet's location in a habitable zone can only hint at the exciting possibility of the presence of the building blocks that create the basis for the complex chemistry of life. While we wonder whether the planet's atmosphere might contain a protective layer like ours, or whether it's a dense, oppressive cloak trapping heat as a result of the greenhouse effect, and what the planet's chemical composition actually is, one thing we know for sure, the last, fourth parameter necessary for life, is in almost perfect agreement. The complexity of life must necessarily be fueled by energy, and the presence of Kepler-22b in the habitable zone ensures its constant supply from the host star. This energy, which powers photosynthesis on Earth, could drive the fundamental biological processes necessary for life on this distant planet. The characteristics of a star that is slightly cooler and smaller than our Sun, but similar in many ways, provides a stable source of light and heat. Against the grand landscape of the cosmos, Kepler-22b stands out as a beacon of possibility. A world where the basic ingredients for life as we know it can come together. Yet the true nature of this distant planet remains shrouded in mystery, reminding us of the vast unknowns that await us as we continue to search for the secrets of the universe and the potential for life beyond our solar system. The search for signs of extraterrestrial life is the cornerstone of our celestial explorations, compelling us to venture into the unknown with hope and scientific rigor. As we turn our eyes toward distant worlds like Kepler-22b, the next generation of telescopes and space missions are poised to pierce the cosmic veil, inviting us to peer into the atmospheres of these distant planets and learn their secrets. At the forefront of this cosmic quest is the James Webb Space Telescope, the most sophisticated and powerful space telescope ever built. With unprecedented resolution and sensitivity, the JWST is designed to observe the universe in the infrared, enabling it to detect the faint reflections of light from the earliest stars and galaxies and, crucially, the atmospheric signatures of exoplanets. The JWST suite of instruments carefully analyzes light passing through the atmosphere of exoplanets as they transit their host stars. This process, known as transmission spectroscopy, will allow scientists to decipher the composition of the atmospheres of these worlds in search of characteristic signatures of molecules essential for life, such as water vapor, oxygen, and methane. The mission of the Transiting Exoplanet Survey Satellite, or TESS, launched in 2018 and complementing JWST, is to survey the brightest stars near Earth for transiting exoplanets. Building on the legacy of the Kepler mission, TESS is casting a wider net, revealing many new worlds for further study. Among them, planets that share characteristics with Kepler-22b will be prime targets for detailed atmospheric analysis, opening up new opportunities to search for biosignatures. Coming down to Earth, the Extremely Large Telescope, or ELT, which, when completed, will be the world's largest optical telescope, will be another powerful tool in the search for alien life. The ELT's colossal mirror, located atop Cerro Armazones in Chile's Atacama Desert, will collect light from distant exoplanets, allowing direct images and spectroscopic studies of their atmospheres. Its advanced instruments will be able to detect even the faintest chemical fingerprints, further expanding our understanding of such distant worlds. Looking ahead, proposed missions such as the Habitable Exoplanet Observatory, HABEX, and the Large UV Optical IR Surveyor, LUVOIR, promise to push the boundaries of exoplanet research even further. Equipped with advanced technology such as coronagraphs and star shades, these observatories aim to directly image exoplanets by dissecting their light to reveal the molecular composition of their atmospheres in unprecedented detail. The hunt for alien life embodied in exploring such planets continues to inspire and stimulate the human spirit, reminding us that the search for life beyond Earth is more than just a scientific endeavor. It's a profound exploration of our place in the cosmos. As we stand on the threshold of discovery, our thoughts drift to the distant world of Kepler-22b, a planet in the nourishing embrace of its star's habitable zone. Here, in this hypothetical realm, we imagine the possibilities such a world might hold. Could it be that the hilly landscapes of this distant planet are home to a diversity of alien flora thriving in the soft light of Kepler-22? Could it also be that its seas are teeming with life, with forms both strange and outlandish, adapted to the unique conditions of this distant world? And what is humanity's potential role in such a world? For now, it's hard to imagine, but these dreams are underpinned by the relentless pursuit of knowledge that defines our current path in exoplanet exploration. As we gaze into the heavens with instruments such as the James Webb Space Telescope, the Transiting Exoplanet Survey Satellite, and the upcoming Extremely Large Telescope, we continue to push the boundaries of our understanding. Each discovery adds its own piece to the great puzzle of the cosmos, revealing the diversity of worlds that inhabit our galactic neighborhood. The future of exoplanet exploration promises to deepen our understanding and knowledge of distant worlds and redefine our place in the universe. As we stand at this crossroads of imagination and discovery, we remind ourselves that the search for life beyond Earth and the understanding of humanity's future potential among the stars is a reflection of our deepest desires to explore, understand, and reconnect with the vast, wondrous cosmos that is our home. Is the fabric of our universe woven with the threads of time travel, or is it a tapestry of unattainable dreams? Our documentary series embarks on a quest through the corridors of science and imagination, probing the boundaries of what we understand about the cosmos and our place within it. Can we bend time to our will, traversing the past and future as easily as we journey from one destination to another? We explore the tantalizing concept of time travel, delving into the realms of physics and fantasy to uncover whether our universe harbors the potential for such extraordinary journeys. What barriers stand between us and the realization of a warp drive, a technology that could tear through the cosmic speed limit set by Einstein's theory of relativity? We investigate the scientific hurdles and breakthroughs that tease the possibility of faster-than-light travel, asking what's stopping us from building a warp drive. In the cosmic ballet, where stars are born and black holes devour, the concept of white holes presents an intriguing counterpoint, an impossible possibility that challenges our understanding of astrophysical phenomena. Could these theoretical reverse black holes exist, ejecting matter and light into the universe, and what would their discovery mean for our understanding of cosmic evolution? Finally, we turn to a groundbreaking discovery, a new law of nature that bridges the gap between physics and biology, offering a framework to predict the course of evolution itself. How does this new law of nature redefine our understanding of life's complexity and its interplay with the physical universe? Join us as we navigate these profound questions, seeking answers at the intersection of known science and speculative theory. This series is an invitation to journey beyond the horizon of current understanding to ponder the mysteries that lie at the heart of existence. Welcome to a documentary experience where the impossible becomes a gateway to new realms of knowledge. Imagine a canvas of moments woven with the threads of time. Matter that stretches endlessly in all directions, capturing every choice, every event, every heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look into the future, or even change the course of history? Time, it governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debate. But what can science say? Can time travel ever move from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light, but time itself. Did you know that astronauts aboard the International Space Station age slower than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let us journey through the corridors of time. We'll explore the science, paradoxes, and limitless possibilities that may one day make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humankind was fascinated by the heavens and the passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating elaborate calendars and methods of measuring time. Transported to the modern era, this fascination has found a new canvas: film and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that time could be navigated like the dimensions of space. Then came Back to the Future, a pop culture powerhouse that took the concept of time travel and made it accessible to a whole new generation. Who could forget the DeLorean, the magnetic condenser, the flux capacitor, and Doc Brown's charming eccentricity? But it's not just a Western phenomenon. The allure of time travel knows no cultural or linguistic boundaries. From the Japanese Steins Gate to the Soviet Ivan Vasilievich changes profession, the theme of time travel resonates around the world. So what is it that attracts storytellers to this concept? The allure of rewriting history? The excitement of the unknown? Or perhaps the philosophical questions such journeys raise? It's a desire fueled by a mixture of nostalgia and anticipation, a longing to revisit cherished memories or leap into the promises of tomorrow. And as we stand on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we? Should we? And what if we did travel through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like E equals mc squared are not just symbols. They're keys to understanding the universe. But can they unlock the secrets of time travel? From silver screens to living room TVs, time travel has been portrayed in countless ways. But let's peel back the layers of fiction and delve into the science that can make time travel more than just a plot device. Meet space-time, the four-dimensional fabric of our universe. According to Einstein's theory of relativity, this fabric can be bent and deformed by mass and energy. But can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of motion or the gravitational field. For example, astronauts on the International Space Station age slightly slower than people on Earth. Experiments with particle gas pedals and atomic clocks have provided empirical evidence of time dilation. It's been observed that particles traveling near the speed of light decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that could theoretically allow time and space to be shortened. Although somewhat speculative, the math suggests that they are possible. Leading physicists and cosmologists have voiced their opinions on the matter, offering theories that range from plausible to downright bizarre. Some even suggest that quantum mechanics, the science of the very small, may play a role in making time travel possible. And let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space but time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of causality. They say time goes forward, always forward, and never backward. But what if we could leap forward, skipping years, decades, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the main parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already been done, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age a little slower than their counterparts on Earth. Let's turn our attention to the twin paradox, the famous thought experiment that takes time dilation to a new level. Imagine twins separated at birth. One travels through space at near light speed, while the other remains on Earth. Upon reunion, the space twin will appear younger. Achieving speeds close to the speed of light would greatly enhance this effect. However, such speeds are currently beyond the reach of our technology. Not to mention the energy requirements would be astronomical. Scientists and engineers are wrestling with these problems, researching propulsion technologies that could, one day, make near light speed travel possible. But even then, can the human body withstand such a journey? Imagine a future where time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of free will? From science fiction to science articles, wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time may turn out to be the cosmic shortcuts we've been dreaming of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch, and then poking it with a pencil. In space-time, the wormhole would be that pencil, creating a straight path between 2 distant points. This concept gained traction in the scientific community thanks in part to Carl Sagan. While writing his novel Contact, he consulted with physicist Kip Thorne to explore the scientific possibility of using a wormhole for interstellar travel. Today, physicists are delving deeper into the math of wormholes. While the general theory of relativity allows for their existence, the equations also assume that they collapse too quickly for anything to pass through them. Theoretically, by introducing some exotic matter, for example, it could counteract the gravitational forces causing the wormhole to collapse, keeping it open long enough for something or someone to pass through. The portrayal of wormholes in popular media often glosses over these complexities. They're usually portrayed as stable, luminous vortices. But the reality, if they exist, can be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer modeling and indirect observations to understand their properties and potential uses. Imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present, the other in the future or the past. The implications for research and even for preventing global catastrophes are staggering. Wormholes open the door to questions not only about where we might go, but when. And as we approach the potential discovery of these cosmic shortcuts, we must ask ourselves, are we ready for the responsibility associated with such power? In the world of the very small, where particles are also waves, and reality itself seems blurred, lies the quantum world. Could this region of uncertainty hold the keys to unlocking time travel? Quantum mechanics challenges our everyday understanding of the world. Take the two-slit experiment, in which particles behave as both particles and waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that's been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics may offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers as if they're ghosting through walls in the two-slit example. Can a similar principle enable time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable to classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for today's computing machines. The concept of quantum entanglement adds interest. Imagine two particles cooked together in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly stunning aspect of entanglement is that the state of one particle instantly affects its entangled partner, regardless of the distance separating them. This could be across the room or even across the galaxy. Change the spin of one, and the other instantly changes. Albert Einstein famously called it spooky action at a distance. At first, he didn't like this idea because it seemed to violate the limit of the speed of light set by his theory of relativity. Since then, however, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could such an effect at a distance make a difference to instantaneous time travel? While the intersection of quantum mechanics and time travel is still in the realm of speculation, it is a hotbed of scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Imagine a future in which the principles of quantum superposition could account for multiple timelines or realities. What if you could exist in a superposition of past and present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Moving on, let's move from the world of the microscopic scale to the grandiosely large one, black holes. mysterious titans of space whose gravity is so strong that not even light can leave them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves. A closed time-like curve, or CTC, is a path in spacetime that loops back on itself. Theoretically, an object or even a person traveling along a CTC could end up in an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. Gödel's solution to Einstein's field equations suggested that rotating universes could contain paths looped in time. However, these solutions required certain conditions, such as a universe filled with rotating matter. Although Gödel's model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which STSSs could exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. Massive gravitational and rotational forces can theoretically twist space-time into loops, creating CTCs. But there's a catch. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped rather than point-shaped. This ring feature could potentially serve as a gateway to the CTC. However, powerful gravitational forces could also create a barrier, known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with paradoxes and uncertainties. For example, if CTCs exist, they can lead to paradoxes in which cause and effect are reversed. This has prompted some physicists to propose the chronology defense hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Would we ever be able to navigate safely through such a treacherous region of space-time? And if we could, what would we find on the other side? Another universe? Another time? In addition to black holes and closed time-like curves, there's another cosmic mystery that could potentially open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe may be remnants of the Big Bang itself. Cosmic strings are thought to have formed in the early moments of the universe as they cooled down after the hot and dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense, and would have had a tremendous gravitational pull. Although still theoretical, cosmic strings offer intriguing possibilities for time travel. Physicists J. Richard Gott and William Hiscock have made significant contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could theoretically distort spacetime enough to create a loop allowing time travel into the past or future. However, the existence of cosmic strings is still a matter of debate. Their detection would require astronomical observations on scales that are currently beyond our capabilities. Moreover, if they do exist, harnessing their power for time travel would be a challenge. Now, let us return to quantum entanglement. We've already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be bound in time? Some theories suggest that entangled particles can be used to transmit information not only in space, but also in time. Imagine a future in which quantum entanglement is used to create a kind of quantum internet that allows instant communication across eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics rife with unanswered questions and untapped potential. Researchers are exploring how the two phenomena might be connected and what this might mean for our understanding of time travel. Imagine a scenario in which cosmic strings are manipulated at the quantum level through entanglement. This would represent a merger of the very large and the very small, a meeting point of cosmic and quantum scales that could revolutionize our concept of time travel. As we venture into the realm of time travel, we face many paradoxes and riddles. These are not just intellectual exercises. They are fundamental questions that can make or break the possibility of time travel. First of all, this is the grandparent paradox. Imagine going back in time and not allowing your grandparents to meet. If they never meet, one of your parents will never be born, and therefore neither will you. But if you were never born, how would you even be able to travel through time? The grandfather paradox raises questions about causality and the nature of time itself. Some theorists suggest that such paradoxes can be resolved through the existence of parallel universes, where each solution generates a new timeline. Another confounding bootstrap paradox is named after the popular expression, pulling yourself up by your bootstraps. Imagine going back in time to give Shakespeare a copy of your works, which he then claims as his own. Where, in that case, did these works originate? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox, the paradox of predestination, is when a time traveler's actions in the past lead to the very event he was trying to prevent. This raises questions about free will and determinism, and whether we can ever really change the course of history. The study of time travel paradoxes is not just a playground for philosophers. It's a serious area of research in physics and metaphysics. The resolution of these paradoxes may shed light on time travel. While we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching the realm of real science. From cosmic strings to quantum entanglement, from spinning black holes to closed time-like curves, we explore the theories and possibilities that could one day make time travel a reality. Current research is paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we ready for what we might find? Time waits for no one, but what if we could wait for time? For years now, there's been a concept that defies the very laws of physics as we know them. A dream that has spawned countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could potentially allow us to travel vast distances in space faster than light itself. Imagine a journey where time and space constraints yield to the power of human ingenuity, where the farthest corners of the universe suddenly become accessible. This isn't just science fiction. It's a puzzle that scientists have been piecing together for decades, ever since physicist Miguel Alcubierre proposed a theoretical model in 1994. Alcubierre's model, a bold combination of imagination and Einstein's theories, offers a way to bend the fabric of space-time itself. But what lies behind this bold idea? Is it a mere flight of fancy? Or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and breakthroughs surrounding warp drive. From the mysterious nature of negative energy to the tangled horizon problem. So let's dive into the depths of one of the most intriguing scientific quests of our time. The quest for the warp engine. Science or fiction? In the heart of Mexico City, amidst the hustle and bustle of city life, a young mind was fascinated by the mysteries of the cosmos. We're talking about Miguel Alcubierre. Born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and led him to the prestigious University of Wales, where he delved deeply into the fields of general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a breakthrough in world perception that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's break down the Alcubierre drive. Imagine a spaceship that does not move through space in the usual sense, but sits in a space-time bubble. This bubble, or deformation bubble, is the key to the Alcubierre concept. According to Einstein's general theory of relativity, massive objects distort the fabric of spacetime. Alcubierre hypothesized that if we could manipulate spacetime in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing the bubble forward. Behind it, space expands, pushing it from behind. Inside this bubble, the spaceship remains stationary, but the bubble itself moves, allowing the ship to move faster than light without violating the laws of physics. This idea doesn't involve moving the spaceship at high speed. Rather, it's about moving space around it. It's like putting a surfboard, a spaceship, on a wave warp bubble and letting the ocean, space-time, carry it. However, the Alcubierre model is not simply a manipulation of space. It requires exotic matter with a negative energy density to stabilize the warp bubble. This exotic matter is one of the many theoretical obstacles scientists face as they try to turn the Alcubierre drive from a fascinating theory into reality. Delving deeper into the practical aspects of the Alcubierre drive, we're faced with huge challenges that stand between theory and reality. The first of these is the scale of energy and mass requirements. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably huge amount, far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. An outstanding achievement was when physicist Chris van der Broek proposed modifications to the shape of the warp bubble. These adjustments dramatically reduced the energy requirement to about the mass of 3 suns. Still a colossal amount, but a significant step down from the original estimates. The second major obstacle is the need for exotic matter and negative energy. In the Alcubierre model, this exotic matter is crucial to stabilizing the warp bubble and making it function as intended. Negative energy is a peculiar and controversial concept. It's a concept in physics that can distort the very fabric of spacetime. It's not just the absence of energy, but an actual physical quantity with negative characteristics. In the context of Alcubierre drive, negative energy will counteract the effects of normal positive energy, creating the conditions necessary for the existence and stability of the warp bubble. Negative energy, in the context of Alcubierre drive, is indeed a complex and somewhat elusive concept in physics, and it's important to distinguish it from the more familiar concepts of gravitational potential energy. In classical physics, the concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, like a planet, is considered negative energy because it takes to move the object from the source of gravity to a point where this energy would be zero, for example, to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, the negative energy required for the Alcubierre drive is different. In this context, negative energy refers to a hypothetical form of energy whose energy density is less than zero. It's not just an accounting tool or a way of describing potential energy in a gravitational field, but rather a real physical substance or field with exotic properties, such as repulsive gravitational effects. This type of negative energy is not something we observe or well understand in the context of known physics. However, the existence of negative energy and, by extension, exotic matter remains a topic of intense debate and speculation in physics. Although phenomena such as the Casimir effect suggest the possibility of the existence of negative energy under certain conditions, harnessing it on the scale required for warp drive is a challenge. These challenges, the enormous energy requirements, and the need for exotic matter, underscore the monumental task of transforming Alcubierre drive from a theoretical model to a practical reality. They represent not just technological obstacles, but fundamental questions about the nature of the universe and our ability to manipulate its basic forces. As we move forward into the world of warp drive technology, we face another obstacle known as the Horizon issue. This issue is at the heart of the Alcubierre drive design and poses serious problems for its practical application. In astrophysics, the horizon is often referred to as the boundary beyond which events cannot affect an outside observer. The most famous example is the event horizon of a black hole, the point of no return. Beyond this horizon, the gravitational attraction is so strong that nothing, not even light, can leave it. Similarly, in Alcubierre drive, the horizon is the boundary of a warp bubble. Inside this bubble, the spaceship is cut off from the rest of the universe, just as the interior of a black hole is isolated from the outside world by its event horizon. The horizon problem arises from the unique structure of the warp bubble itself. In the Alcubierre model, the spacecraft is located in a region of the space-time plane surrounded by a warp bubble that compresses space at the front and expands it at the back. This manipulation of space-time allows travel at speeds faster than the speed of light, but with a critical limitation. It isolates the spacecraft from the rest of the universe. Imagine being inside this warp bubble, the very mechanism that allows you to travel vast distances in space also prevents you from controlling the ship or interacting with the outside world. Communication signals, navigation commands, and even visual observations are all prevented by the bubble's boundary. Passengers and crew will not be able to control the spacecraft, correct its course, or even stop the journey once it's begun. The implications of the horizon problem are profound. It implies that a spacecraft driven by warp would essentially be traveling on a one-way, uncontrolled journey. This raises practical questions about using such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with celestial objects or adjust our flight path to meet unforeseen circumstances? Moreover, this problem implies the need for a pre-established infrastructure, similar to an interstellar highway, with mechanisms to create and control the warp bubble from the outside. Such a requirement adds another layer of complexity to the already difficult task of realizing warp drive technology. While the horizon problem represents a significant engineering challenge, it is important to recognize that it doesn't invalidate the fundamental scientific validity of the concept. Theoretically, the principles underlying the warp drive remain unchanged and plausible within the framework of the general theory of relativity. As we delve deeper into the complexities of Alcubierre drive, we encounter another major problem: the radiation problem. This problem is twofold. It involves both the accumulation of radiation at the front of the deformation bubble and the potential effects of Hawking radiation within the bubble itself. First, let us consider the radiation accumulating at the front of the warp bubble. As the bubble moves through space at a speed faster than the speed of light, it inevitably encounters interstellar particles and cosmic radiation. These particles and radiation, unable to bypass the warp bubble, accumulate near its front end. Such accumulation poses a significant risk. When the warp bubble slows or stops, the collected radiation and particles will be released in a burst of energy. The intensity of this release could be catastrophic, not only endangering the spacecraft and its passengers, but potentially damaging any nearby objects at the destination. Moving inside the warp bubble, we encounter the second aspect of the radiation problem: Hawking radiation. This theoretical radiation, predicted by Stephen Hawking, arises from the effects of quantum mechanics near the edges of black holes. In the context of Alcubierre drive, the intense warping of space-time around the edge of the bubble could create conditions similar to those at the event horizon of a black hole, potentially generating Hawking radiation. This radiation could have harmful effects on passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are profound. Not only do they pose serious engineering and safety challenges, but they also raise questions about the feasibility of long-duration travel using Alcubierre Drive. Ensuring passenger safety and spacecraft integrity in the face of these radiation hazards is a critical area requiring further research and innovative solutions. It is a challenge that requires ingenuity and a deeper understanding of the interplay between quantum mechanics, the theory of relativity, and the harsh reality of space travel. When we turn our eyes to the current state of research in warp drive technology, we find ourselves in the thick of scientific research. Recent years have seen a flurry of theoretical papers and articles that break new ground in this field. One notable development has come from the work of physicists who've been revisiting the energy requirements of the Alcubierre Drive. Based on earlier advances that significantly reduce the estimated energy requirements, recent papers have proposed various methods to further optimize the geometry of the warp bubble. These improvements are aimed at making the energy requirements even more feasible, approaching the realm of possibility. Significant contributions to the field have been made by researchers such as Harold White, who was instrumental in the experimental work on the feasibility of deformation bubbles and space-time manipulation at the NASA Eagle Works laboratories. Another area of active research is exploring alternative theories that could circumvent some of the limitations of the Alcubierre Drive. For example, some physicists are exploring the possibility of using solitons, solitary waves that retain their shape while traveling at a constant speed, as a basis for creating stable strain bubbles without the need for negative energy. There's also growing interest in the role of quantum mechanics in warp drive physics. Researchers are delving into the quantum aspects of space-time and how they might affect warp drive mechanics. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the warp bubble. Recent theoretical advances also include the study of the effects of warp drive technology on causality and the fabric of space-time. These studies are critical in addressing potential paradoxes and time travel scenarios, ensuring that the concept remains grounded in physical laws as we know them. Little by little, the dream of warp drive technology is moving ever closer from the pages of science fiction into the realm of scientific possibilities, driven by the tireless efforts of researchers around the world. As we ponder the future of warp drive technology, we find ourselves at a crossroad of assumptions and possibilities. The realization of warp drives, a concept once confined to the realm of science fiction, depends on several key developments and breakthroughs. First of all, the theoretical problems associated with warp drive technology need to be addressed. This includes finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. Advances in areas such as quantum mechanics, exotic matter, and energy manipulation are critical to turning these theoretical possibilities into practical reality. Beyond the scientific and technical obstacles, the advent of warp drive technology brings with it many ethical and practical considerations. The ability to travel vast distances in space at unprecedented speeds would revolutionize space exploration, opening new horizons for humanity. However, with great power comes great responsibility. The ethical implications of such technology must be carefully considered. This includes the potential impact on space ecosystems, the responsibility to explore and possibly interact with extraterrestrial life, and equal access to this technology among nations and peoples. In practice, warp drive technology could lead to new methods of resource utilization, new ways of conducting scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space. from one of exploration to one of habitation and utilization. For now, we look forward to a future in which stars are not just points of light in the night sky, but destinations within our reach. This future promises uncharted territories and unprecedented exploration, beckoning us to continue our quest for knowledge and discovery. There's an interesting mystery in our world, generated by the equations of Einstein's general theory of relativity. It's the theoretical analog of the black hole familiar to many. We call it a white hole. Imagine a region of space where, unlike an all-consuming black hole, nothing can penetrate. Instead, this cosmic anomaly defies our expectations by ejecting matter and energy, glowing violently on the dark canvas of space. In a universe governed by the concept of an arrow of time, where events flow from past to future, a white hole is a tantalizing paradox. It's like watching a space movie in reverse, where the rules of gravity and time seem to be rewritten. But are these celestial wonders just mathematical curiosities? Or do they hold the key to understanding the deeper truths of our universe? Let us delve into the mysteries of white holes, exploring their theoretical underpinnings, their enigmatic characteristics, and their potential role in the great history of the universe. In the early 20th century, Albert Einstein revolutionized our understanding of the universe by creating the general theory of relativity. This groundbreaking theory proposed a radical idea. Gravity is not a force pulling objects together, but rather a curvature of space-time caused by mass and energy. Imagine space-time as a fabric stretched like a cosmic trampoline. When an object of mass, such as a star or planet, lands on this fabric, it causes a dip. This curvature directs the motion of other objects, which move along curved trajectories in space-time. This is gravity, as Einstein envisioned it. Einstein's theory led to the prediction of black holes, regions in space where the gravitational pull is so strong that nothing, not even light, can escape. These cosmic giants form when massive stars collapse under their gravity, distorting space-time to the extreme. Introducing Carl Schwarzschild, a brilliant physicist who, while fighting in World War I, found an interesting solution to Einstein's equation. Schwarzschild's solution described space-time around a spherical, non-rotating mass, such as a star. Schwarzschild's work laid the foundation for understanding black holes, but it also hinted at something even more mysterious. If a black hole is a region from which nothing can escape, could its polar opposite exist? A region where nothing can enter, but only leave. This led to the birth of the concept of a white hole. Just as a black hole is the end point of gravitational collapse, a white hole can be thought of as a reverse black hole, a cosmic fountain ejecting matter and energy. However, unlike black holes, which have already been observed, white holes remain a theoretical concept, a tantalizing possibility in the vast cosmic mystery. In the field of astrophysics, the path from mathematical abstraction to physical reality is often long and difficult, and white holes are no exception. These theoretical entities arise from the complex equations of the general theory of relativity, the same mathematical structure that predicts the existence of black holes. The math of white holes is robust, but it's like a jigsaw puzzle with missing pieces. We understand their theoretical basis, but the real challenge is to relate these mathematical models to observable phenomena. Imagine a universe in which, instead of collapsing inward, a region of space-time does the opposite. It explosively ejects matter and energy. This is the essence of a white hole, a mirror image of a black hole, in which the flow of time and matter is reversed. But can these mathematical abstractions exist in our physical reality? The debate among scientists is ongoing and multifaceted. Some theorists suggest that white holes may be remnants of the early universe, exotic structures woven into the fabric of space-time itself. Others suggest they may represent the other end of a black hole, a kind of cosmic exit door from which matter and energy reappear after being swallowed up by the black hole. The novel idea of quantum gravity suggests that as a black hole evaporates over many epochs, losing mass, it may reach a point at which it can no longer sustain itself as a black hole. At that point, it may turn into a white hole, releasing the trapped contents back into the universe. However, there are serious problems with the physical existence of white holes. The laws of thermodynamics, especially the concept of entropy, presents a serious obstacle. Entropy, a measure of disorder, tends to increase in the universe. White holes, by their nature, decrease entropy, which contradicts this fundamental principle. Moreover, the stability of white holes is a controversial issue. Some theories suggest that if they did form, they'd be extremely unstable and would probably collapse almost instantaneously into black holes. In outer space, white holes represent one of the most enigmatic and paradoxical concepts. These mirror images of black holes have characteristics that challenge our traditional understanding of physics. Let us understand in more detail what is the concept of a white hole in theoretical physics. At the heart of a white hole is its event horizon, a boundary not of inescapability, as it is with black holes, but of impenetrability. This event horizon marks the point where matter and energy are ejected, creating a spectacle of cosmic proportions. Unlike a black hole, which takes over everything, a white hole is the source of the expulsion, the cosmic fountain from which matter and energy arise. One of the most intriguing aspects of white holes is the concept of time reversal. In the universe, time usually flows in one direction, from the past to the future. However, white holes seem to reverse this flow. It's like watching a space movie played backwards, where the usual rules of time and space are reversed. Deepening into the nature of white holes, we face a realm of paradoxes and problems. One of the most important is their connection with the previously mentioned entropy. According to the second principle of thermodynamics, entropy, or the measure of disorder, should always increase in a closed system. However, white holes seem to ignore this law, decreasing entropy and ejecting matter in an ordered state. This apparent violation of thermodynamic laws presents a serious problem for our understanding of physical processes in the universe. How can such an object as a white hole exist if it contradicts such a fundamental principle? Another paradox lies in the concept of the arrow of time. Where the universe moves inexorably forward in time, white holes suggest a scenario in which time can flow backward, at least from a certain point of view. This concept breaks not only our understanding of time, but also the very nature of causality in the universe. Let us summarize the characteristics of white holes, their event horizons, the expulsion of matter, and the concept of time reversal present a fascinating but paradoxical picture for theories that, while we're looking to solve these problems, white holes remain in the realm of theoretical physics. As we delve deeper into the mysteries of the cosmos, the concept of white holes invites us to rethink our understanding of the universe. These theoretical objects are not just surprising anomalies. They may have profound cosmological implications. Consider the Big Bang, the colossal explosion that marked the beginning of our universe. Some theorists suggest that this pivotal moment in cosmic history was not just a random explosion, but that the event may have been a white hole of unimaginable magnitude, an eruption of matter and energy that gave birth to the cosmos. This view offers a radical new interpretation of the origin of our universe, suggesting that white holes may play a role in cosmic genesis. Imagine a white hole not just as a theoretical construct, but as the very source of the creation of our universe. In this scenario, the Big Bang could be envisioned as a white hole of unfathomable scale, spewing out matter, energy, and space-time that subsequently evolved into the stars, galaxies, and planets we observe today. This view offers a radical rethinking of the Big Bang. Instead of an undefined singularity, we have a white hole, an entity defined by the laws of physics, albeit in a form that stretches our understanding to its limits. This white hole may have been the first spark that set the stage for subsequent cosmic evolution. If the Big Bang was indeed a white hole, it raises profound questions about the nature of our universe. What was the source of this white hole? Was it the result of a collapse of the universe from another dimension, or the result of processes beyond our current scientific understanding? This concept also changes our perception of time and causality. If the Big Bang was a white hole, it suggests the existence of a universe with a more complex timeline, in which the beginning and end of cosmic phenomena are intertwined in ways we've yet to understand. This idea of the Big Bang as a white hole organically combines with the Big Bounce theory, according to which the beginning of our universe may be the result of the collapse of the previous universe. It unites the idea of cyclical universes, suggesting that each cosmic end can give rise to a new beginning, similar to the explosive genesis of a white hole. The existence of white holes may also confirm the concept of parallel universes. If white holes can eject matter and energy, could they be a gateway to other universes? This possibility is related to the multiverse theory, which postulates the existence of multiple, possibly infinite universes, along with our own. In parallel universes, there may be different versions of physics, alternate histories, and perhaps even variations of ourselves. Another intriguing connection relates to wormholes, hypothetical tunnels in space-time. Theoretical models suggest that wormholes could link distant regions of space and perhaps even different universes. If white holes are connected to wormholes, they could serve as cosmic portals, opening paths to remote corners of the universe or other dimensions altogether. This connection raises tantalizing questions about the nature of space and time. Could white holes and wormholes allow travel over vast cosmic distances, or even between different universes? Looking into the future of astrophysics, we see that at the moment there's a lot of scientific research in one way or another affecting the subject of white holes. But two research papers stand out among the rest, shedding light on the mysterious nature of these cosmic objects and offering new ideas and possibilities that could revolutionize our understanding of white holes. The first paper takes us on a journey to the very edge of black and white holes, exploring the close connections between them and refocusing on the physics occurring near their horizons. The authors introduce the concept of horizon-penetrating coordinate systems, a revolutionary approach that allows us to distinguish between the horizons of black and white holes. They differ from standard curvature coordinates in a small near-horizon region to emphasize the distinction between black and white horizons, which depends on near-horizon physics. This study suggests that black holes may not be the cosmic dead ends we once thought. Instead, they may be in quantum superposition with white holes, creating a scenario in which observed phenomena may hint at the existence of these theoretical white counterparts. The paper also delves into the role of quantum physics in these near-horizon regions, suggesting that quantum effects may dominate, leading to significant implications for our understanding of white holes. However, the authors emphasize that there's a problem in observational astrophysics, in which there is substantial observational evidence for black holes, but relatively weak observational support for white holes. Moving on to the second paper, titled New Black-to-White Hole Solutions with Improved Geometry and Energy Conditions, we find that the focus here is on the way to convert black holes into white holes, guided by the principles of quantum gravity. This study presents models in which the effects of quantum gravity prevent the formation of singularities inside black holes, providing a smooth transition to white holes. This solves the long-standing paradox of information loss by assuming that matter can pass through a black hole and appear in a white hole. The paper also explores geodesics within these models, confirming the completeness of particle trajectories in the transition from the black hole region to the white hole region. This supports the idea of a continuous, unimpeded flow of matter, changing our understanding of these cosmic phenomena. By integrating these theoretical developments with emerging technologies, we stand on the threshold of a new era in astrophysics. The future of white hole research promises to reveal new aspects of the universe where the boundaries between quantum mechanics and general relativity are blurring. To summarize, we can say that the future of white hole research is very bright. Who knows? Perhaps very soon, we'll be able to discover indirect evidence for the existence of these intriguing objects. Our universe hides a mystery that's long captivated the human mind. A question that bridges the gap between the known and the unknown, the simple and the complex. Here on Earth, life thrives in a continuous movement of order and chaos. Every form of life is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammals. But what if the complexity of life, the very essence of our existence, could be explained not only through the lens of biology, but also through a mathematical framework? This is the territory of assembly theory, a groundbreaking concept that transcends traditional science. It's a journey into a world where math and biology converge to reveal the hidden architecture of life. Imagine a universe in which the secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and are waiting to be decoded, where the line between living and non-living is blurred, giving birth to new possibilities and new understanding. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. And maybe we can even get closer to answering the ultimate question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been the language of the universe, a tool for deciphering the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life? At its core, assembly theory offers a simple but profound idea. The complexity of life can be measured and understood through a mathematical prism. Think of life as a jigsaw puzzle, where each piece represents a molecular building block. Assembly theory seeks to show how these pieces come together step by step to form the complex structures that define living organisms. Each step in this assembly process represents a leap of complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index. The assembly index, the cornerstone of this theory, measures the number of steps required to build a biological structure. It's a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit into this? This standard model theory of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from the complexities of biology. However, assembly theory bridges this gap. In the field of assembly theory, the standard model lays the foundation for understanding forces and interactions. It's a bridge between the microscopic world of quarks and leptons and the macroscopic world of living things. Another important element of the theory is the concept of studying dynamical systems, phase space. This is a mathematical concept used to describe all possible states of a system. In the context of assembly theory, phase space allows us to map the path of the assembly of life. From a single point representing the simplest form of life, phase space expands, branching out into almost infinite possibilities. Each pathway representing a different route that life can take. In this limitless mathematical landscape, the paths of evolution and its complexities unfold. This mathematical framework gives us a new perspective on the complexity of life. It's not just about the particles and forces described by the standard model, but how these elements combine and interact over time to create the diverse pattern of life we see around us. This is where the chaos of random molecular interactions gives way to the order of living structures. So let's ask ourselves this question: are the complexities of life simply the product of chance, or is there a deeper cause? Let us consider two sharply contrasting concepts: complexity and entropy. Entropy, a measure of disorder and randomness, seems to be at odds with the complexity we observe in life. How do these opposing forces coexist in the natural world? It's here that assembly theory offers a revolutionary perspective. So, central to assembly theory is the assembly index, a revolutionary tool designed to measure the complexity of life. Think of it as a cosmic ruler, measuring the steps required to assemble a biological structure from its simplest components. Imagine a single molecule as the starting point on this scale. As you move up the scale, each step represents a more complex assembly, from molecules to cells and beyond. The higher the index, the greater the complexity, and the less likely it is that the structure could have arisen by chance. Now let's delve into the interaction between entropy and complexity. Entropy, a concept rooted in thermodynamics, suggests that systems naturally tend toward disorder. However, life defies this tendency, evolving from simple origins to a variety of forms combined into the complex ordered structures we see today. How does assembly theory resolve this apparent contradiction? It suggests that life is inherently a process of overcoming entropy. Through the lens of the assembly index, we see the complexity of life is not a challenge to entropy, but a journey through it. Consider the early Earth, a primordial soup of simple molecules. Over millennia, driven by the laws of physics and chemistry, these molecules began to assemble into more complex structures. Each step along the way marked a victory over entropy, a step toward greater complexity in life. Rethinking evolution through assembly theory, we see it not as a mere biological process, but as a mathematical inevitability. The emergence and evolution of life became a story of increasing complexity, a story written in the language of mathematics. Let us now turn to a very trivial question, but one that shines in a new light. Are we alone? The search for extraterrestrial life has captivated our imagination for centuries. Now, thanks to assembly theory, we have a new tool in this cosmic quest. Assembly theory offers a unique approach to detecting alien life. It's not about scanning the sky for radio signals or analyzing light spectra for the presence of oxygen. Instead, it's about understanding the complexity of molecules and structures that may indicate life. Imagine scanning the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of the samples in search of patterns that indicate the presence of life. The higher assembly index, the more likely it is that these molecules are the result of life rather than random processes. However, the road to discovering alien life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know. Life on Earth. What if it doesn't meet our biochemical standards? Another problem is the vastness of space. The universe is vast, and our ability to explore it is limited by current technology. Even with sophisticated telescopes and probes, we can only analyze a tiny fraction of the cosmos. Moreover, assembly theory, while powerful, is still in its infancy. It's a new approach, and its application to the search for extraterrestrial life is uncharted territory. There are questions about its applicability and accuracy in different environments, especially those that are very different from terrestrial environments. Despite these problems, the potential of assembly theory in the search for alien life is enormous. It could redefine our understanding of life in the universe, opening new doors in astrobiology. So assembly theory offers a new way of looking at life, not just as a biological phenomenon, but as an emergent property of cosmic complexity. Imagine the early days of our planet, a world in motion, a crucible for the chemistry of life. Here in this chaotic environment, simple molecules began the journey of assembly, a process governed by the laws of physics and chemistry, but leading to something much deeper. Life, according to assembly theory, emerges when these molecular structures reach a level of complexity that allows them to store and reproduce information. This is where chemical memory, a crucial step in the evolution of life, comes into play. Chemical memory is the ability of certain molecular structures to retain structure. In other words, we can say this is the blueprint for life. In the world of assembly theory, this is where reproducibility becomes key. The ability to reproduce these patterns, to pass them on from generation to generation, is what drives the evolution of life. From the simplest RNA molecules in the primordial soup to the vast diversity of life we see today, each step in this evolutionary journey has been a step up the assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not just a story of increasing complexity. It's also a story of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the depths of the ocean to the fringes of space. In the realm of scientific discovery, every new theory is scrutinized and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, now stands at a crossroads, being questioned by critical voices such as Dr. Hector Zennel. The critique presented by Zennel raises fundamental questions about the future evolution of assembly theory. Covering an impressive 18,000 words, the article will require time and thought, taking approximately 1 to 2 hours of dedicated reading. This is not a cursory look at the topic, but a deep dive into the heart of the scientific debate. For those who are interested, we leave a link in the description to both articles, the study and the counter-arguments to it. Looking to the future, the role of assembly theory in scientific research remains uncertain. Will it be able to adapt and overcome these challenges? Or will it remain a footnote in the history of science? Despite the disagreements, one thing is clear. The debates surrounding assembly theory have initiated a conversation about the nature of scientific discovery. They emphasize the need for transparency, rigor, and humility in pursuing knowledge. In the end, the impact of assembly theory on future research may not lie in its specific claims, but in the lessons it teaches us about the scientific process. As we explore the mysteries of life in the universe, such theories will come and go. But the quest for understanding, the quest to unlock the mysteries of our existence, will always remain at the center of the interest of scientific research.